Hello, I am Professor S. Shankaran in the Department of Metallurgical and Materials Engineering.
Rotations and the specimen is being held by the grips as well as the load. A lot of weights depending upon the test conditions. The specimen is subjected to 4-point bending, and in view of the rotation, the specimen experiences a sinusoidal variation of stress levels of equal magnitudes in tension and compression. So you have to remember, in fatigue loading, since it is called the cyclic loading, so the load given in one direction in tension will be completely reversed to the other direction. That's why it is given in this typical fatigue test is done by tension compression mode. For a given load, the number of cycles at which failure occurs is noted, and the data is collected for various loads. So that is one very basic way of recording the fatigue data. A log plot of stress applied and the number of cycles to failure establishes the existence of endurance limit for a given material. So this is a stress versus number of cycles to failure, which is plotted in a log plot. And here you see that the material, after certain stress levels, the material does not fail. So this stress is called endurance limit of the material. We will look at that aspect little in the next chapter in much more detail, but here we will connect it to only fracture mechanics. Questions to be answered for a fracture mechanics based design. One of the mechanisms of crack growth is by fatigue. In structures subjected to fatigue loading, if a crack is detected by NDT methods, as a designer one should know how to react to the situation. The questions to be answered are: is it safe to operate the component or machine? If safe, for how long? Is it possible to monitor the crack growth so that one can discard the component or stop the machine before catastrophic failure can occur? So these are all crucial questions. And what are the limitations in fatigue test? Inherent flaws grow due to fatigue crack growth mechanism and reach a critical level which leads to fracture. The concept of endurance limit, cyclic stress level permitted to a life of 10 to the power 7 cycles or more, has been able to give a conservative estimate of life of component. So any component which subjected to cyclic stress, which can endorse this many number of cycles, then that is it's a benchmark so far. But modern design do not take this value. It is much more stringent value, but still this was one stage it was considered as a endurance limit life. However, the SN diagram cannot provide answers to crack growth or inspection intervals, as no attempt is made to detect or monitor the crack growth. A more exhaustive test needs to be done to answer these difficult questions. One of the standard specimens for fracture testing is fatigue loaded, and the crack growth is monitored by NDT methods. The fatigue loading is not fully reversed as in fatigue test, but the lower load is kept zero in these tests. Okay, we are now talking about a crack growth curve, how it is normally done. The experiment is repeated for various loads, and a plot of crack length versus number of cycles is obtained. And the plot looks like this: fatigue crack length in mm versus elapsed cycles in thousands. So you can see that such a very less number of cycle, the specimen failed. That means you can see the load delta P is very high load, 44.1 kilonewton. So as you keep on reducing the load, the life also keep on increasing. And this is typically for a nickel molybdenum vanadium alloy steel tested at 23.9 degrees centigrade. Test frequency is 1800 cycle per minute, and crack growth is a function of cyclical load and crack length. Okay, so this is what it is, a typical curve. The point is, as you keep on changing the load, you will get n number of curves for a given material. So this is something you have to think about it. So what Paris has done, Paris observed that the data from the crack growth test for a given material could be represented as a single graph if one plots the graph in log scale between dA by dN versus delta K. So what you see here in this plot is crack growth rate dA by dN, that is micrometer per cycles, and versus the stress intensity factor range, that is delta K, MPa square root meter. It's a straight line. So this is for again different loads, and this is the dA by dN is equal to C into delta K to the power m. So this equation is called a Paris law. The observation of Paris is an important step in modeling crack growth by fracture mechanics. So it's a huge jump to understand the crack growth behavior. That is quite obvious because if you look at the previous slide, for a given material you can generate n number of crack growth curves. So it will be then too difficult to handle such a huge data for a given material, and it will be very difficult for designers to engage them. So the Paris law gives a very important step in modeling the crack growth behavior that way. So now let us look at the details. The approach is purely empirical because it is simply a curve fitting, but then it is very intelligently done, but quite simple to model a complex phenomena. Okay, very complex. And the ingenuity of Paris law is that the effect of applied stress and the crack length on crack growth rate is intelligently modeled by a single parameter delta K. That is very important point to note. His original work appeared as a Boeing technical note. The role of environment was not considered, and this enabled Paris to arrive at a simple empirical relation. Environment has got a significant influence on crack growth rate. If it was also attempted to have been modeled, then we would not have arrived at Paris law at all, because that kind of significance the environment has. Paris law is elegant, and corrections are incorporated to this model. The role of environment later, that was a development of Paris law. And how was this Paris law validated? Because people raised a lot of questions before they really applied to use this in the design aspects. And then there are some verifications. Does loading configuration affect the Paris law? That's a question. How do we test this? How do we test? Donaldson and Anderson collected crack growth data for two entirely different configurations. One is a center crack subjected to a wedge load, where the stress intensity factor decreases as a function of crack length. The other is a central crack panel subjected to a far field stress, where the stress intensity factor increases as a function of a crack length. So there are two extreme cases. Then they have applied this Paris law to their experiment and then see what they get it to, so that they can validate it. So for a specimen A, they have taken K max versus crack length, which is given by this K1 is equal to P by square root of pi A, which goes like this. And specimen B is K1 is equal to sigma square root of pi A as a function of A by W, which goes like this. So in one case, stress K max decreases, the other case K max increases. But both the data is now for these two different specimens are plotted in this fashion: delta K versus dA by dA. The relationship between the crack growth rate and the stress intensity factor range is essentially the same for these two loading configurations. So that means the these two different specimen configuration, what you see here is the almost a similar trend. So that means the Paris law is valid even for different specimen loading history. So how to get the experimental procedure to get the crack growth rate curve? So this is a CT specimen, and then this is an NDT probe which will monitor the growing crack, and then A versus N plot are generated and for different loads, and then you plot the log dA by Tn versus log delta K, then you get a straight line. So that is, then you obtain the material constant C and M. Okay, so this is how it is done. It is well known that many famous materials exhibit unlimited fatigue life, provided that the stresses are within the endurance limit. This indicates that very short cracks may not propagate for small values of delta K. The smallest value of delta K for a crack propagation is known as threshold stress intensity factor, very important parameter in fracture mechanics as well as fatigue. It is a characteristic of a material, and it has got lot of influence on the fatigue behavior as well as the fracture behavior. We will look at that in detail in the coming slides. At the other extreme, when delta K becomes comparable to the fracture toughness of the material, the crack growth rate becomes very large. So this also we will see in the crack growth curve characterization. Fatigue crack growth threshold delta K TH for a selected engineering alloy. So you can see that mild steel, and this is aluminum alloy. You can see that delta K threshold is 6.6 MPa for mild steel, and this is for other alloy which is given. This is an R value. This is a K minimum by K max. This R is different from what we have seen in resistance in fracture mechanics. And now what we will see is a schematic representation of fatigue life showing the relative proportion of life for a crack initiation and propagation. This plot I showed in the introduction slide, introduction chapter, where the stress versus life is plotted. The crack initiation period is much larger as compared to crack propagation period. First of all, we have to recognize that there are two stages or two components to the life. One is initiation period and the another is a propagation period. So this is very important. Okay, this is a fatigue limit. Sigmoid curve. So this is typical fatigue crack growth curve, dA by dN versus delta K in log scale. You can see that this curve is being divided into three regions for its geometry. You can see that this is a delta K threshold, and this is a region 1, and the region 2 is a kind of a straight line. This is a crack growth region, region 2 and region 3. The shape of the crack growth rate curve from the crack initiation to catastrophic failure is a sigmoidal curve. Very important curve for engineering and design. So the region 1 is characteristic of the following. Region 1, this is a region for micro crack growth. So, you can always see that this threshold, that means the crack initiation phase. So all the cracks will be in the micron level. Crack growth is extremely small of the order of nanometers and not uniform over even small distances along the crack front. Hence, the fatigue striations are not formed. Microstructure, mean stress, and environment have a large influence in this region. Very important point to know. Maximum life of the component is in this region. So the maximum life is crack initiation. That's what we have just seen in the couple of slides back. So maximum life of the component is spent to reach the delta K threshold. That's important point. Note. And now the region 2 is so-called the Paris region. Crack growth rate is of the order of 10 to the power minus 4 mm per cycle to 10 to the power minus 2 mm per cycle. This is the rate. And fatigue striations are formed in this stage. So it is shown here. You can see that the fatigue striations. Paris law is applicable only in this region because that's a straight line. Microstructure has small to large influence depending upon the material. So you cannot say that it is not having any, microstructure do not have any role to play. We cannot say that. But depending upon the material, either it has a small or a large influence. That's what we have to understand. Certain combinations of environment, mean stress, and frequency have a significant influence. And in this region where the crack growth can be monitored by NDT. So because it is a steady state growth, so it can follow the Paris law, and then it can be nicely monitored by an NDT technique. Region 3, the crack growth rate is very high, of the order of 10 to the power minus 2 mm per cycle to 10 to the power minus 1 mm per cycle. Crack runs through entire grain in one cycle. Microstructure, mean stress, and thickness have large influence, and environment does not play a significant role in this region as compared to the region 1. This is completely opposite. Component needs to be discarded if the crack growth reaches this stage. So it's almost a dangerous situation. So that is where you have to decide. So there are several other models to improve upon the Paris region proposed by several researchers. Some of them I am just giving just for the information sake, not to get into the detail. And similarly, there are, if you look at the region, that was region 1, and this is given by other scientists, Forman law for the region 3, dA by dN is given. And then later you will see that it is entire sigmoidal curve is given by other people for this kind of an expression. And we are not going to discuss all of them, just to give you an impression that the Paris law has been developed and then modified, and then they have been used at different, they have been used effectively to monitor the crack growth behavior. That is the information I want to convey. Okay. So the next important topic we are going to is stress ratio. That is R. I showed in the table K minimum by K max. That is called a stress ratio. K versus number of cycles. So normally a fatigue loading is in this cycle. In this particular case, R is greater than 0. R is defined as sigma minimum by sigma max, which is K minimum by K max. And R is called the stress ratio. And then you have the second type of scenario where R is equal to 0, where the cycle K versus N plot will look like this. There is another scenario, R is equal to -1. Then the positive and negative values of K will go through in the cycle as a function of number of cycles, and clash of symbols between the fatigue and fracture. So that's what I just mentioned. R in a fracture is a resistance. Here it is a stress ratio, and this is for R is greater than 0, R is equal to 0, R is equal to -1, under which the fatigue testing can be done with the different stress ratio values. The mean stress influence on fatigue crack growth is given in this plot. So you keep just changing the value of R, then you are essentially looking at the mean stress influence. And what you will see here is the curve keep on moving to the left hand side, but not significantly important in this Paris region. But it has got some influence again on the region 3. Okay. So what we can see here is the mean stress influence is significantly happening in the region 1 of the sigmoidal curve and the region 3. That is how you should take it. Okay. Now, very important aspect of fracture mechanics as well as fatigue is the crack closure. So we are now talking about we have been talking about the crack growth and its stability and where it reaches a catastrophic limit and all that. But we should also now talk about crack closure. Okay, this is also a very important idea which will influence on the fatigue life as well as fracture mechanics analysis. Elber in 1970 demonstrated through a set of carefully planned and experimental investigations that a fatigue crack propagating under the 0 to tension loading, that is R is equal to 0, might be partially or completely closed at 0 load. Okay. This observation has led to a new concepts in fatigue crack growth studies. Very important idea. Okay. So how do we understand this? To account for a crack closure, designers employ a modified Paris law, which is as follows: dA by dN is equal to C times delta K effective to the power m. So delta K is being now replaced by delta K effective. So how do we understand delta K effective? Suppose this is a K versus T plot. So this is a cycle, sigmoidal cycle. So the moment the stress reaches this level, that means the crack start opening, then it goes further and then it comes back. So when it comes back, again it will close, right? Then it will open, reaches maximum, close, close again, reach open, reaches maximum, close, something like that. So where C and M are material constants and delta K effective gives the effective range of stress intensity factor. So delta K effective is K max minus K opening. So this distance is the delta K effective, where K max is the maximum stress intensity factor and K opening is the value of K1 when the crack opens completely during the load cycle. So this is how you have to understand this designer's approach of crack closure. Elber also provided fractographic evidence to show that crack closure could affect the shape of the striation pattern. The striation peaks are flattened due to deformations during crack closure. One of the important issues is how to estimate K open. So how to estimate K opening? The value of K opening is not a material constant but depends on the number of factors. Different alloy exhibit different closure behavior. Even for a given alloy, the closure behavior is different at different loading regions. So these are all some limitations for this proposals. Nevertheless, it was practiced with some limited experimental conditions. So there are some empirical relations given for engineering alloys. For example, T3 aluminum. Elbert reported that delta K effective by delta K is equal to 0.5 plus 0.4 R for the stress ratio in range of 0 to 0.7. Okay, the other people have also given similar empirical relations for the crack closure study. So let us look at what is the current focus. A great deal of effort has been taken by various researchers to measure, characterize and predict crack closure behavior and its effect on the crack growth rates. A majority of this research has been experimental in nature. One of the main difficulties in experiment is obtaining the information of displacement histories at midsection in a thick specimen. It is challenging as it is not easily acceptable. Okay, so that is one problem. So the current focus is on developing appropriate numerical models to study the phenomenon. Study of effect of T stress, that is sigma OX for the, this is a terminology for the photoelasticity. T stress on fatigue crack closure using FEM is recently reported by Roy Chaudhary and Dodds. So this is something currently it's going on in the recent times. And then we will now look at the types of crack closure. One important classification is plasticity induced crack closure, where you are going to look at the residual stress ahead of the crack in a cycle. So what you are going to see here is you see the crack tip and there is a plastic zone. This is a material plastically deformed, and the surrounding region, what is given is elastically deformed. Okay, because of these two, different zones, typically residual stress is generated in this region. Elastic zone springs back when the load is released. In the process, introduces a compressive load on the plastically deformed portion. Okay, so this is well understood, and because of that, you get this kind of a residual pattern generated. Residual compressive stress is here, and this is a residual tension. So you see that this kind of residual pattern, and the presence of residual compressive stress retards the crack growth. So this is the ultimate idea. The sense the plastic zone ahead of the crack tip, okay, facilitates in retarding the crack growth. So that is one very important idea. So this also will induce, this plasticity also will induce the crack closure. That's what we are discussing here. So if you look into the details, in a growing fatigue crack, behind the crack tip a plastic wake is developed. So how do we understand this? How it grows? So this is an initial crack length, and then this is a plastic zone. If you look at the animation carefully, so every time it completes a number of cycles, the plastic wake region is also getting increased. Elber postulated that crack closure is due to the existence of residual strain in the plastic wake. So there is a large amount of strain in the region of plastic wake. So that residual strain, okay, which is responsible for the crack closure, that is proposed by Elber. This is one model. And another thing is, here is a crack, and then around this crack you have the plastic wake, and then plastic zone is formed here. So we can consider this as a strip of material along the crack edges, though no longer loaded but has undergone plastic deformation. Previously constitutes the plastic wake. Yeah, we can consider like this. When the load is reduced due to the permanent elongation of the crack lips, they close before the load is zero. So this is one way of looking at it. You can see that the load is not yet reached 0, but even before it's 0, you can look at this green mark here. The crack is closed because of the plastic wake. So this is one way of understanding how the plasticity induced crack closure happens. At zero load, typical residual stress pattern is shown here. So here again you can see that the residual pattern is it is completely compressive here, and this is a tension. Okay, so this is in view of this, crack faces do not open until K reaches K open. Okay, so because of this residual stress development, it does not open until it reaches the stress K open. So that way it is quite interesting to note that plastic deformation helps in closing the crack. The next one is phase transformation induced crack closure. The residual strain developed as a function of as a result of a phase transformation produced by an applied stress also causes crack closure. Okay, this is similar to the plasticity induced crack closure. So you can see that the new phase which is formed around the crack tip is will create a similar residual stress pattern like your plastic wake. Before even it reaches 0, it try to close the crack. So similarly, any phase transformation also will cause this. In material science, this is quite popular in improving the fracture toughness of ceramics. I will discuss that in the next chapter, and I will bring this idea. So here it is just discussed in the very generic manner. We will take it. We will take up the specific example and then discuss this. And wedge-induced crack closure is another mechanisms, which is also known as oxide-induced crack closure, usually associated with aggressive environment. That quite obvious, right? The oxide has to form, and then that will facilitate the crack closure measurement. So that means it is essentially happening in the aggressive environment. The corrosion products become wedged between the crack faces. This is very quite popular mechanism in the fatigue. So you see that the crack extension is shown like this, and some of the corrosion products are sitting like that, and they are all going to act as a wedge between these two surfaces. Before the load reaches 0, they are going to kind of get wedged between these two surfaces. So this is considered as an oxide induced crack closure. And in the similar way, the roughness induced crack closure is also quite popular. Microscopic roughness of the fatigue fracture surface causes this. At the microscopic level, due to the microstructural heterogeneity, mixed mode conditions can exist. The displacement due to the mode 2 can cause mismatch between upper and lower crack faces, contributing to the crack closure. So mode 2 is a sliding mode. So obviously it will help us to realize this kind of crack closure mechanisms. Very straightforward idea. Okay. So now we will look at influence of overload on the crack growth, and this is also very important mechanisms. Probably we will just discuss in the next class. Okay, probably I'll stop here, and we'll continue in the next class. Thank you.